Okay, so we're on page 13, and the point of this is to try and determine whether a solution is saturated. These questions, they're no different really, but they're just worded slightly differently. But again, you're working with whatever solubility value that you have. So have a look at this question. It says, a solution was prepared by mixing 15 grams of potassium nitrate with 50 grams of water at 30 degrees C. Determine whether or not the solution is saturated. What does it mean if a solution is saturated? Good. So it can't dissolve anymore. Or it is dissolved as much as it can. Alright, so the first thing we need to do, as with all these calculations, is go and find our solubility value at that temperature. So your table of results is on the previous page, at the bottom of page 12. So what is your solubility value at 30 degrees C? Yeah, great. It's 36 grams per 100 grams of water. Okay, and what that value tells me is that if I had 100 grams of water, the maximum that could dissolve in it would be 36 grams. But the problem is, I don't have 100 grams of water. I only have 50 grams of water. Okay, so I need to calculate the maximum mass that will dissolve in 50 grams of water. How do I do that? Not divide by 36 and times by 50, divided by... Good. So always look at the mass of water that you have. So you're taking your 36 and either just divide by 2, that's the quick way of doing it, but just in case you get an awkward value, you're dividing by 100 and timesing by 50. And so that's going to give you 18 grams. So what that is telling me is that the maximum mass I could dissolve in 50 grams of water is 18 grams. But look back to my question then. It says that I have prepared this solution by adding 15 grams. Okay, so is it saturated? Okay, so look what we calculated here. The maximum mass which can dissolve is 18 grams. So it's not saturated because I've only added 15 grams. So this is not saturated. So again, there's a couple of different ways you can do this question, but this is the best way to kind of keep it similar to our other calculations. Look at your solubility value and then change it for whatever mass of water that you have. And then bear in mind what your solubility value tells you is the maximum mass that can dissolve in that mass of water. So how many more grams could dissolve in our solution? 3. Perfect. 3 grams more. And if you want to say how we got that 3, you just do 18 minus 15, which is 3. Okay? So what I want you to do is have a practice at a couple of those questions. I might take you through the first one, and that would be going back to page 21. And it's part F of question 4. Okay, so this is a very similar question. It says 9 grams of potassium chloride were placed in 20 grams of water at 40 degrees C. The solution formed was described as saturated. And we have to explain why that is. And again, it says it's worth 1 mark. This question would be worth more than 1 mark. The important thing that we need to start with is, what do we always do at the very start of these calculations? Yeah, good. You write down your solubility value at that temperature. Okay, so what we need to do is go to our graph for this, which is a couple of pages previously. And we need to find the solubility value at 40 degrees C. So if you go to your graph now, the graph that you drew on Friday. Yeah, perfect. So your solubility, that's what we want to write down first of all. Solubility at 40 degrees C is 40 grams per 100 grams of water. What does that tell me? Put it into words. What does that mean?
For 100 grams of water, you can always dissolve 40 grams of potassium chloride.
Perfect. Absolutely perfect. Okay. But the problem is here, I only have 20 grams of water. Yeah, it is. Okay, so then I need to work it out in 20 grams of water. You could even write maximum mass. Pretend I didn't hear that. That can dissolve in 20 grams of water is going to equal, how am I going to do this? So take my 40 grams and I divide it by, yep, I can either divide it by 5, or how do I do it the longer way? Divide by 100 and times by 20. That's the longer way around to do it. Okay, and that gets you 8 grams. And what the 8 grams is the maximum, and as we said at the start of the line there, the maximum mass that can dissolve in 20 grams. So if the maximum mass I can dissolve in 20 grams of water is 8 grams and I have 9 grams, then so that explains why this solution is saturated, because I've added 9 grams and it's only 8 grams is the maximum that can dissolve in it. So if I'm asked to calculate the mass which remained at the bottom, okay, so I added 9 grams in, the maximum mass that can dissolve is 8 grams. So that leaves me with 1 gram at the bottom. So the last type of calculation that you need to be able to do is to work out solubility values when the mass of water used is not 100 grams. So up to now we've been plotting graphs and our solubility values have always been in grams per 100 grams of water. So for example, your solubility value might have been 30 grams per 100 grams of water. What that means is that 30 grams is the maximum mass of solute which will dissolve in 100 grams of water at that particular temperature. But when determining solubility values, sometimes experimentally it's easier to use a smaller mass of water. So for example, we might find that 2 grams dissolves in 10 grams of water, and that's the solubility. What we need to work on doing now is converting those into solubility values, which are always in per 100 grams of water. And essentially what we're trying to say is, whatever I need to times my mass of water by to get to 100, so in this case it's very easy. I obviously need to times by 10 to get 100 grams per water. I then times my mass of solute by that same factor. So the solubility for this salt would be 20 grams per 100 grams at that particular temperature. The long way round of doing that is dividing by the mass of water that you have. So dividing by 10 in this case because I had 10, and then multiplying by 100 to get the values in 100 grams of water. Either way you do it this way, it's going to make no difference. You'll get the same answer, because 10 divided by 10 here is 1 times 100 is 100. So I have to do the same thing to my mass of solute. 2 divided by 10 is 0.2 times by 100 is 20 grams per 100 grams of water. And the reason we need to do it the long way around sometimes is because sometimes our value of water is, our mass of water is not an easy value like 10 scaling up to 100. For example, in this case, we have 2 grams of potassium chloride dissolved in 4 grams of water. And it might be quite hard to think, well, what do I need to multiply 4 by to get to 100? So what we do is we divide our mass of solute by the mass of water used, and then multiply by 100 to get our value. And if you did it for this one that's been done for you, you would get that answer. 2 divided by 4 is 0.5 times by 100 is 50. So your solubility value is 50 grams per 100 grams of water. So here we've got the one that we have to fill in, we need to do our mass of solute, which is potassium chloride, divided by the mass of water that we have, which is 5 grams, and then times by 100 to get it in per 100 grams of water. 2 divided by 5, if we fill in our working out down here, 2 divided by 5 is 0.4. And then our next step is to multiply that by 100. 0.4 times by 100 is 40 grams per 100 grams of water. And I can fill that in my table, 40.0. Question 6 on page 22 has a similar example to this. And the start of the question describes an experimental technique used to determine the solubility of this potassium nitrate salt. We have been used to using the same mass of water, so 10 grams of water, and changing our value of the solute. But here what they've done is they've kept the mass of solute constant, and they've used a different mass of water each time. But in order to be able to compare these solubility values, they need to be in the same unit, in grams per 100 grams of water, not 10 grams per 8 grams, 10 grams per 10 grams, 10 grams per 12 grams. That wouldn't make much sense. So in order to convert our values and plot our graph, we need to get them in grams per 100 grams of water. So again, we take our mass of solute, we divide by the mass of water, and we times by 100. So in this first example, if you wanted to write your working out at the side, you're doing 10 divided by 8 and times by 100. Put that into your calculator and you should get 125. Do it for the next value then. Again, we're doing 10 grams divided by our mass of water, which is 10, and then times by 100. So we're doing 10 divided by 10 times by 100, which gives us 100. The next one, exactly the same. We're doing 10 divided by 12 and then times by 100. Which gets you 83. And you can continue on and use that same method. But in order to scale it to 100 grams, divide by the mass of water that you had and times by 100. So this is on page 15. And the first 2 bullet points just tell you about the solubility of a couple of different gases. And the first examples being oxygen, carbon dioxide and hydrogen. They're not very soluble in water, and what that means is we can collect them over water. And you may have seen this done in year 8 to 10, just where you produce a gas and then you can collect it, and if you turn a test tube upside down, fill it with water, you can fill the test tube with that gas because the gas doesn't dissolve in the water. And then you've got other gases that are actually very soluble in water as well. That's in your second bullet point there. But that's not too important. What's more important with this idea of solubility of gases is how solubility of gases changes as temperature changes. So when we had looking at the solubility of solids, so normal salts, what happens to the solubility as temperature increases? Solubility increases as well. Okay, great. What we find with gases is that it's the total opposite of that. For most gases, as temperature increases, the solubility decreases. And how that has an effect is on this thing called thermal pollution, and that's what's really important in this part of the topic. You may get asked a question on this. And it's just the idea that as you increase the temperature, as water gets warmer, you can't dissolve as much gas into it. It's why your fizzy drinks, when you take them out from the fridge and they're really cold, they're really fizzy, because they've got lots of gas dissolved in them. But if you leave your drink out at room temperature, as it warms up, it'll become flat over time, and that's because not as much gas can dissolve into it. So that's why that is. But what is important for your exam is this idea of thermal pollution. And so what happens is we have factories. I'll try and draw a wee factory here. Okay, that's my factory. we'll have a chimney and some smoke as well. Okay, and what you'll find is that a lot of factories are close to lakes and bodies of water in general, and that's because in factories you're using machinery and it gets very, very hot, and so what they do is they use water from lakes to actually cool down their machinery. So what they're doing is they're taking this water, they're putting it around their machinery, cooling the machinery down, but what happens then to the water? Pardon? Yeah, it gets polluted. How? So thermal pollution, it's a kind of special type of pollution. With heat, yeah, okay. So as my water cools down the machinery, what is happening to the water, the temperature of the water? Yeah, it's getting hotter. So what they're going to do is they're going to pump that hot water back into the lake. So the temperature of the lake gradually increases. And what that has an effect of doing is, if you think of in the water, fish can breathe because there's oxygen dissolved in the water. That's how they breathe, through their gills. And they don't breathe water, they breathe oxygen. They just happen to breathe it through the water. And it's the oxygen that's dissolved in the water that they need. So as the temperature increases in the lake, the solubility of oxygen is going to decrease. So as that lake gets hotter and hotter, there's less and less dissolved oxygen in it. So what do you think is going to happen to the fish? They're going to die. It's really sad. So yeah, the fish die due to lack of oxygen. So this comes up quite a lot actually, and there's a past paper question about a goldfish bowl, about why you don't put it next to a radiator. So you need to talk about the water, temperature of the water increasing, and therefore the solubility of oxygen will decrease. Therefore there's going to be less oxygen in the water. So fish die due to lack of oxygen. And your typical question is there with your mark scheme answer. So it's definitely something that's worth learning. It would be a 3-mark question if it came up. But there's your points there. The solubility of oxygen decreases as temperature increases. So the fish die from lack of oxygen. So just at the end there, you have your summary of comparing how the solubility is affected by temperature. So with solids, what happens when temperature increases? What happens to solubility? It increases. So with solids, the solubility tends to increase. Think again about your sugar in your cup of tea. You can dissolve more sugar in it when your water is hot. Whereas with gases, it's the opposite. So as temperature increases, the solubility of a gas decreases. Okay.